Arthur Samuel, this guy over here on the right-hand side, in 1959, he is the first person who coined the term machine learning. And according to him, machine learning is a field of study that gives the computers the ability to learn without being explicitly programmed. Without explicitly programmed here means without directly telling what needs to be done. But this definition of machine learning is a bit too broad, in a sense that how do we know whether the machine actually learns or not? To give more context, in 1997, Tom Mitchell redefined machine learning. A computer program is said to learn from experience E with respect to some task T and some performance measure P if its performance on T as measured by P improves with experience E. To put it simply, there must be a way to measure the performance of the machine learning model. For this, we are going to use this spam email detection as an example. I'm sure most of us have email. Either we are using Gmail, Yahoo, or even our university email. The moment we open up our email, we can see a lot of folder, right? The inbox folder, the send folder, then we get a trash folder, and then we have one that is what we call the spam folder. So the experience here is where the user will label the email as spam or not. Sometimes when we receive email and then we see that it doesn't look good and it doesn't look right, and we will check that email and then put it into our spam folder. The task of this spam email detection obviously is to classify the email as spam or not. And the performance of the spam email would be the number of emails that are correctly classified as spam or not spam. In machine learning, there are three types: supervised, unsupervised, and the last one we have the reinforcement learning. Supervised learning, as the name defines, means direct supervision. It's like spoon feeding. It's just like on the first figure here on my left-hand side. We directly tell the kids what needs to be done. We put a shape. If you see a shape that looks like a circle, put it over here. If you see a shape that looks like this, put it to a top right. If you see a shape that looks like this, put it at the bottom left, and so on. This is what you call a supervised learning. You directly tell the kids to arrange the blocks based on the matching shape. Unsupervised learning, as the name defines, un means not supervised. That means without direct supervision. This time, we will leave out for the kids to figure out how to arrange the blocks. They can arrange the blocks based on colors by putting black at one corner, red at the other corner, yellow in another corner, and so on. Or they can arrange the blocks based on the shape: square at one corner, circle at one corner, and so on. And the third types of machine learning is what we call the reinforcement learning. Reinforcement learning is based on trial and error using feedback. Just like in the last figure over here. Every time when the kid do something, we will feedback, regardless whether it's right or wrong. If it's right, we just tell the kid, well done. If it's wrong, then we will feedback to correct the kid. So this is how reinforcement learning is based on feedback. It learns. And this picture here shows the overall summary of the three types of machine learning: the supervised, the unsupervised, and then the last one, we have the reinforcement learning. This particular class, we are concentrating on the supervised learning, okay, this part of here. Within supervised learning, there are two types: regression, and then we have classification. Regression, generally, we are trying to predict numerical outcome. For example, we want to predict the house price in this particular area. Classification, on the other hand, is to predict categorical outcome, like those yes or no. Example, do you have COVID? Yes or no. That is example of classification. So today, the focus of this class is on the classification method. Let's take a look a bit more on the classification. The example that we used in earlier, the spam email detection, this is an example of classification. In classification, we have what we call a target class. Now, this is important, yeah, because anytime when we do classification, we need this target class. This target class is also called as dependent variable. And usually, this target class is denoted by the variable y, and this is the variable that is to be predicted. If you take a look at this table at the bottom here, the one that is highlighted in yellow, the last column, this is what we call the target class, the one that we want to predict. In this example, we want to predict whether we want to play tennis or not based on the weather. So this is the weather, yeah, the outlook, the temperature, the humidity, and also the wind. And this is what we call the independent variable. And the one at the last column, this is what we call the dependent variable. And the last column is the one that we want to predict whether we want to play tennis or not based on the weather. The goal of classification is to train a model on the set of record with known classes, that means the target class. Then we apply the model for prediction. So just recap a bit, whenever time when we do classification, we need a data set that contains the target class. Without target class, we cannot do classification. And today we're going to take a look at 3 commonly used methods: decision tree, k-nearest neighbor, and artificial neural network. We'll begin with decision tree, the first method. And this is how a decision tree looks like. Just like imagine that we have gone to an interview and we want to decide right now whether to accept this new job offer. So obviously, as being human being, right, the first decision that you want to decide whether to accept the job offer is your salary. So of course, our decision would be, is it at least 50,000 or not? If it's not, then no, we are definitely strictly going to decline that. If yes, it's at least 50,000, the next decision we will make is whether the commute time, is it more than 1 hour? I'm not too sure about the traffic in Kota Baru, but in KL, the traffic is fantastic. Okay, we can really, we sometimes the traffic can be crazy. It can be more than 1 hour, even though a short distance. To me, commuting more than 1 hour is a big no. So I will definitely decline the offer if it's commuting more than 1 hour to the job. The last decision would be, is the company offering free coffee? If yes, most likely I will accept the offer, but if not, then we will decline. A decision tree, as you can see a lot of nodes, right? The one in blue color, this is what you call a decision node. And this is where the decision is made. The one in green, okay, this one here, this is what we call the leaf nodes. This is where the outcome, whether to accept or decline the offer. In decision tree, it's just like a flow chart, right? Just like here in this tree example, it's just like a flow chart. It consists of sequences of nodes, the decision nodes, and the leaf nodes. And you can see from this decision tree here, it's very easy to understand, very easy to explain. And that's why decision tree is one of the commonly used methods in machine learning. To understand a bit on our decision tree, let us do some gameplay. Okay, don't worry, this is a very simple game, yeah. Over here, we have a list of cars. I think it's about 11 cars. For each car, we have already specified, yeah. I will tell you the brand, the model of the car, the CC of the car, and the price of the car. You can ask me any 3 questions. After the 3 questions, you need to guess what car I have in mind over here, one of these cars. You can ask me any question, okay? We will just assume that all these cars, they are gray in color or silver in color. They are having the same colors. To make things more challenging, you can only ask those questions where I can answer yes or no. Example, if your question is the car having 4 tires? Then my answer will be yes. If you ask me question like, is which country the rim of the car imported from? That one will be disqualified because I cannot tell you exactly the country. I can only answer you yes or no. So ask only those questions that is either yes or no answer. So let's try. The 3 question is not 3 questions from each of you. 3 questions is from all of you. So after that, you need to guess and tell me which car I have in mind. So who would want to go first?
Can I go first?
Yeah, can. But before that, disclosure a bit. Let me share with you a bit. I'm not a car person, yeah. So you can ask me very general, like very general things that I can try to help to answer. But if you ask me very specific, like this engine in this particular parts, is it imported from which country or whatever country? That one I might not be able to tell you. What is the RPM of this car when it accelerate from 100 kilometer per hour? That one I cannot because as I mentioned, I'm not a car person. So very simple game playing, yeah. Don't be too into the car, yeah. Okay, maybe Dr. Hafiza, you want to go first?
Is the car a local brand?
Okay, so let me just write down the question. Local brand. Okay, so my answer is no. It's not a local brand. Okay, with this, what is the second question that anyone from the floor would like to ask? Don't worry, this is a very simple game playing, yeah.
Can I try it, Doctor?
Yes, sure, go ahead.
Is the car have a 6-seater?
6-seater, 6, yeah. Okay, so let me just 6-seater car. Okay, I will say no.
Is the car is an SUV or sedan? SUV, is the car is an SUV?
Okay, is the car is SUV? SUV car? No. Are you able to guess? Okay, so let me just go back. So let's is it a local car? No. So you know that it's an imported car. Is it a 6-seater car? No. Is it an SUV car? No. Okay, let's go back and let's try to think a bit. Which car do you think that I have in mind over here?
Mercedes.
Mercedes not. Okay, maybe I'll give you one more question. So what if you can ask one more question? Mercedes is not. Okay, maybe I increase one more question. If you think that is very hard, the 4th question?
Is the car under 2cc, 2-liter engine?
2.2 liter engine.
Is the car
less than 2
less than 2?
2 liter? Is it like this?
Yeah.
Okay, let me see. Okay. Yes.
Okay.
Okay, so now so you know the question, right? You get some information already, right? Okay, let's guess which car.
I go for Honda Jazz.
Okay, Dr. Moon. Jazz. How about Dr. Hafiz? So the first guess was Mercedes. It's not. So next one, the guess is Jazz. Anyone have any other thought?
Almera boleh? Can also.
Almera pun boleh kan? Or Almera. Okay, so either it's Jazz or Almera.
Yeah.
Okay, now let's try. Let's see. What is the car that we have? It's Honda Jazz. Now let's revisit those questions that we asked. Okay, let's revisit here. Which question do you think that is helps you to understand okay, which question will give you the most information when you ask?
The CC and I think a brand.
Okay, the CC and also the brand, whether is it local and brand, right? Okay, let's take a look here, because in the very first beginning, there's a lot of uncertainty. Uncertainty here means we can select this car, it can be this car, it can be this car, it can be all of this, any of this. And the moment when we ask questions, right? The moment we ask whether is it a local brand car, the answer is no. That means all local brand car we can eliminate already. So we can eliminate all these local cars. So potong iris pun buang, all this buang, all this buang. So we are left back with all these cars that are under consideration. Then, of course, the next question was asked whether is it 6-liter. But if you ask is it less than 2 liter, maybe this will provide us more information. So if the answer is yes, so we can eliminate some more, right? So this one we can maintain. This one less than, yes. Some more, what else? This one is, because 2 liter, then this one you can eliminate because C3 is 3.5. This one we can maintain. So after that, of course, some questions can actually help us to eliminate further. Now, from this game playing, all these question and answer, it's based on our logic and reasoning, right? We think, we reason, and we try to find out what is the car. But how do we make it obvious to a computer? How do we let the computer learn from how we think, how we reason? And with this, computer need 2 measurements. One is the measurement of entropy. Entropy is the measure of uncertainty. This is how we compute entropy. Again, don't worry about the calculation. Don't worry about the formula. We will come to take a look at this formula with example later. Just know that for now, entropy is just a measure of uncertainty. Just like in the very beginning, when we play this car, right? At the beginning, the entropy is very high because there are a lot of uncertainty. Okay, as I explained, right? There's a lot. This one can be this car, can be this car, can be this car, can be this car, or this car, or this car. So that is the entropy, the measure of uncertainty. The second measurement needed for decision tree is information gain. Information gain is just like your question. How much gain can I gather when I ask this information, or when I ask this information? How much information I can get? So just like just now when we asked the question, is it a local brand? This provides us a lot of information, right? Because we can eliminate those local cars. Okay, so that is the information gain, the expected reduction in entropy. So this is the formula given to calculate the information gain. Don't need to memorize this formula, yeah? Just get some idea. Later on, we will see with example how to calculate this. Now we are going to take a look at this example. This example is basically we want to decide whether we want to play tennis or not. This is the last column is the target class, and this is the weather, the outlook, the temperature, humidity, and wind. And now we are going to start with the entropy first. We are going to take a look at the target class. We start by calculating the entropy. 14 examples altogether. Altogether in this table, there are 14 records. Out of the 14 records, 9 of them yes. So there are 9 of them yes, yeah. And then 5 of them say no. How to calculate the entropy? Use this formula over here. Minus pi log base 2 pi. It's just that number of example. So we have a 9 yes, 5 is no. So this is the yes part, this is the no. So minus 9 out of 14 example, log base 2, 9 out of 14, minus 5, 14, log base 2, 5 out of 14. This log base 2, why log base 2? Because information is measured in bits. So that's why we use the log base 2. Then after that, once we calculated this entropy, the next thing is to calculate the entropy for each of these variables. I just started with wind, yeah? You can start with outlook temperature, but wind is easier for me to just have a look. So same thing, under this variable wind, we have 2 values, weak and strong. So what we need to do now is just fill up the table. Out of those that is weak, how many yes, how many no? So I just circle those that is weak first, yeah? So either from all this weak, you just identify how many yes, how many no, and then fill up the table accordingly. Same thing for the strong value. There are 3 yes, 3 no. What we need to do now is to calculate the entropy for each of these values. So for the weak entropy, 6 of them out of the 8 examples, we have yes, and 2 out of the 8 is no. So we calculate the same thing for the entropy for the weak, yes, and then no. Same thing go for the strong. We have 3 yes, 3 no. So same thing, plug in, calculate the entropy. This is for the yes part. This is for the no part. Now, then after that, we calculate the gain. Okay, how much gain or how much information we can get by asking the variable win. So let me just backtrack here. This is the formula for the information gain. So basically, we use the entropy S, which is this one here, then minus out the sum of this. Okay, so let me just go through using example. Entropy S, just now we calculated earlier for the target class is 0.94. So therefore 0.94 minus, now this part is for the week. How many weeks? There are 8 of them, right? So 8 out of the total example that we have in the table. So 8 out of 14 multiply with the entropy of week, which is 0.81. Then for the strong value, right? There are 6 of them, 6 out of 14 multiply with the entropy strong, which is 1. So after you plug in and then calculate, this is the gain that you get, 0.048. Then we do the same thing for the next variable, which is humidity. Repeat the same whole process. Out of those that is high, how many yes, how many no. Same thing like what we have done in earlier example. And then do the same thing for the normal. How many yes, how many no. Calculate the entropy for high, calculate the entropy for the normal. Then we calculate the gain for the humidity, and this is what we get, 0.151. So between humidity 0.151 and wind 0.048. Now what it tells you, that means if we ask the question about humidity, it will give us the most information compared to the wind. Just like coming back to this game playing just now, right? Is some of these questions will give us the most information. Some of the question might not give us the most. Maybe it will help a bit, but not much. And this is what the information gain is about, yeah? Now, after we calculate, then this is the wind for the gain, humidity, outlook, temperature. We want to select the one that gives us the most information, right? Out of all this gain, which one gives us the most information?
Outlook.
Outlook, yes, that's good. So Outlook actually provides us the most information. So what happens now? We take the Outlook as the root of the decision tree. Because if the moment you ask Outlook, it gives us the most information already, then that will be the one that will be in the root of the decision tree. Then for these branches over here, all these are the values in your Outlook. So Outlook inside, we have sunny, overcast, rain. So each cabang here, we have sunny, overcast, and rain. Now then, we are not done yet because we need to go through repeat the whole process again. Yeah? So this time, let's take a look at this sunny branch. From the sunny, we want to get those records that is sunny only. Okay, so there are 5 records, right? So simplify. So let me just focus on these 5 records. This time, again, this is the target class. Compute the entropy again for these 5 records. Yeah, we have 3 no, 2 yes. So we just compute this. This is the no, this is the yes, the entropy for this sunny. Then repeat the same whole process for computing the gain for wind, humidity, and temperature. So this is how the calculation works. And again, we choose the one with the highest gain. Okay, so between this value, and this value, which one is the highest? Humidity, right? Okay, yes, good. So humidity will be the next decision. Okay, so here we have the humidity. If the outlook is sunny, the next question we will ask is the humidity. Then we have 2 cabang, 2 edges here. One is the high, one is the normal. There are 2 values, right? So put in the high and normal for the 2 bunches. Now, if you take a look closer at this table, when everything is high, can you see very affirmative, right? The decision is no play. So what happens here? Under the high, we straight away have the leaf node, no. So as long as humidity is high, we are not going to play because it's too hot. And when the humidity is normal, then can you see it's very confirmed we will go and play. So here, there's a leaf node for yes. And this is how the decision tree works, yeah? And then for the overcast, we will back to the original table for 14 records, find those records that is overcast. Then you can see that for the play is all yes. So what happens here? Just put directly the yes for the overcast. And for the rain, this time we are looking for all the rain, records for all the rain. And then just like humidity, repeat the whole process and then find out the gain and choose the one with the highest gain value for the next decision. So this is the final outcome of the decision tree for this table here, yeah, the decision tree that we built based on this table that have 14 records. And you can see that from this decision tree, the first question we should ask is the outlook. If the outlook is overcast, we straight away, yes, we will go and play. If it's sunny, the next question we should ask is humidity. Is it high or normal? If it's high, we are not going to play. If it's normal, then yes, we're going to play tennis. From this decision tree, so let's take a look at this algorithm in a very summarized way. At each node, that means at each part of the tree, we select the best variable. How to select this best variable? The one that gives us the most information. Then we split based on the possible outcome, based on this all these values, and then we repeat this whole entire process, just like what we have seen earlier on, until it has been assorted into a leaf node, until we reach all these leaf nodes. And this is how decision tree works. Just to give you some idea, back end, this is how computer actually learn, use the entropy and information gain to build this decision tree. The one tree algorithm that we actually use, because we're using information gain, the tree algorithm is based on ID tree. ID here means stand for iterative dichotomizer. We just call it as ID tree. There are other different ways to split the branches. So if you are interested, you can take a look at all these splitting criterion like Gini index, gain ratio, chi-square. But the one that is commonly used is the information gain, and normally used in textbook to get started for the decision tree. Then we move on to the second method, the k nearest neighbor. Before I talk about this k nearest neighbor, is there any question about decision tree that you want to ask?
Sorry, can I ask something?
Yes, go ahead.
Back to the chart that we developed before, the sunny
Okay.
day.
This one.
Okay. What happen if after the humidity high, they still have a yes or no under the high?
If that can continue to calculate, so maybe it could be, I don't know, it could be something else. Temperature, it could be later on, maybe got some more, right? Maybe it could be temperature.
So the final decision must have a one.
Until you
yes
reach.
or no.
Yes, until when everything is yes. So, like example, like backtrack to this one, right? As long as, let's say, if all no, then we should already put a leaf node. If they got one yes, one no, then one yes, something like this, right? Then we need to proceed on to the temperature and calculate for this one. It could be the temperature for here, and then temperature we got hot, mild, then we have cool. Then we continue, maybe this one become yes, this one no, or maybe this one continues some more, got some more wind. It could be like this.
So the next branches will be decided based on the value, right?
Then based on the value, then we calculate the value again.
Okay, thank you.
Can, yeah? So normally we will stop as long as it reached the leaf node. But if don't have leaf node, we still continue to calculate the variables. Okay, so that is how decision tree works. That's why the algorithm here, we repeat this whole process until all the test conditions have assorted into a leaf node. If it does not have a leaf node, we continue because maybe who knows they got a lot more cabang later on. Okay.
Dr. Linda.
Yes.
Dr. Linda, sorry. What if the leaf node, the end outcome, have balanced numbers?
Have balanced what? Sorry.
Balanced numbers.
Unbalanced.
numbers.
Balanced number
Balance.
means what?
Means, for example, 2 yes and 2 no. But there's no.
Okay, so let's say, okay, let me just go backtrack to just now, this one here. Okay, let me just erase all this ink. So here you are trying to say that they are uneven, is it, or what?
Even.
Even.
For example,
Oh,
normal.
Okay, so it depends here on whether they got some more variable. If no more variables, then what you can do is, either depending on which tree algorithm, some will just stop it at here. Then we will just randomly take the one with the alphabetically order, so you just put as no. Can?
Okay. Thank you.
Welcome. Boleh ya? Okay, so let me just continue to the next method, which is the k nearest neighbor. The idea of k nearest neighbor, or in short, we call it as KNN, yeah? We want to classify an object based on the majority roots of its neighbor. So if you take a look at this graph over here, there are two different classes. Class A, the one in yellow, class B, the one in purple. And we want to classify this object here, whether is it belong to class A or is it belong to class B. How does the k nearest neighbor work? Basically, we will determine how many nearest neighbor you want to consider. In this example, we want to consider 3 nearest neighbor. When k is equal to 3 means we are looking at the 3 nearest neighbor to this object here. And within this circle, what is the majority? The majority is class B, right? Class B is the majority. So this will be classified as class B. In another example, let's say we extend this. If we are looking at 6 nearest neighbor, okay, 6 nearest neighbor to this object, yeah? Inside this circle, what is the majority? Majority of them is the class A, right? Because the majority of them, they are yellow circle. And this object here will be classified as class A. Let's take a look at the algorithm. For k nearest neighbor, first thing is to compute the distance value between the object that we want to classify with every object in the training dataset. Just like in this example here, to know the distance, right, we need to calculate the distance of this object with this object over here. Distance, calculate the distance, and same thing for this one. All these distances, then we will see which one has the smallest distance to this object. Once we calculated the distance value, then we pick the one closest to the data point, the one that gives us the smallest distance, and then from there, we conduct the majority rule, the majority. How to calculate distance measure? This is the one, the Euclidean distance. So I'm sure this one in high school, lama lagi, right? You already done this before in high school. Just to recall a bit, yeah. On my right hand side, let's take a look at this graph. How to calculate the distance between x and y. If you just to recall a bit, you take this 5 minus 2, and then you square it, plus 6 minus 2, you square it. Then after that, you sum them up, and then you square root the summation value, and then this is the distance of 5. This is the Euclidean distance, and this Euclidean distance is commonly used in k nearest neighbor. Don't worry about this calculation. This one just to refresh you that we have learned this in high school before. And we're going to use this Euclidean distance to help us to calculate the distance measure for the k nearest neighbor. In this example, we have a table on my left-hand side. We have gender, the first column, height, and then we have the weight. If I plot this table here, the right-hand side shows the graph of the plot. On my x-axis, we have height. Y-axis, we have weight. The one in red is the female. The one in blue, this is the male. Now we want to classify this person here. Given the weight height is 170, given the weight is 70. So this person, we want to know the gender of the person. Given that the height of this person, 170, weight is 70. How to calculate this? So first of all, calculate the Euclidean distance of this object with this object. Euclidean distance, calculate for each of these objects over here. Now I already calculated this, and this is the distance that we have calculated between the one in green to all these object data point over here. Once we calculate the distance, next step, we just sort it out in ascending order from smallest to the highest value. Then with this, then we take a look. If we are looking for 3 nearest neighbor, from the table, right? 3 nearest means that the top 3. Take a look at the majority. Is the majority M or F? Is it male or female? Majority is female, so this object here will be classified as female. And if you cannot see from table, let's see from the graph here. The majority, those for the 3 nearest neighbor, is female because majority of them are female. If we want to extend this, k equal to 4, that means that we are looking at the top 4. The majority is female. Okay, if you cannot see the right-hand side in the graph, you can see that from this circle, the majority is female. So this object here, this person here, will be classified as female. And this is how the k nearest neighbor works. So depending on how many nearest neighbor that we are considering, and then from the nearest neighbor, we do the majority work. And then we classify the object based on this majority work. From here, we can see that k nearest neighbor is in fact a lazy learning. Why is it lazy? Because later on, we're doing hands-on, you can see that there's actually no explicit training phase before classification. It's like the whole entire training set is like memorized because you just calculate the distance and then keep it into a table and then use the table to do the majority work. Limitation of k nearest neighbor is that we need to keep this entire training set in memory. Normally, we will use this k nearest neighbor when we have a smaller data set with very less feature. So that is the k nearest neighbor. That is the idea, So just recap a bit. Normally, for k nearest neighbor, we first calculate the distance, and then later on, we choose the one with the closest data point based on the number of nearest neighbor, and then we do the majority work. The simplest algorithm is still workable and still commonly used because it's simple. Okay, that is the k nearest neighbor. Now, any further question on this k nearest neighbor before I move on to the next one, which is artificial neural network?
Prof, can I ask a question?
Yes, go ahead.
Actually, I often heard about the KNN clustering. Is it the same, or is it just another type of machine learning?
K nearest neighbor, yeah, you can usually use for clustering as well. So you can actually use for both for classification and clustering as well.
Oh, okay. It's the same concept, okay.
It's the same concept, yes.
Okay, thank you.
Okay. Okay, so now let's move on to the third one. So we have gone through decision tree. We have gone through the k nearest neighbor. So now the last method will be the artificial neural network. And this artificial neural network that we have is actually inspired by the biological neuron system. And I'm sure that this figure over here is not something stranger to you. I'm sure that as a medical student, when you see this image, I think you will know what is it about. But I still need to explain because our artificial neural network, as I mentioned here, right, is actually inspired from our biological neural system. So help me, if I explain it wrongly, please correct me. Okay, so we have a synapses. Okay, so this synapses is like neurons are connected through this synapses. And then these dendrites here, I assume that these are the inputs to the neurons. And then we have axon, I think the one that transmit the electrical signal, right? From one neuron to another neuron. And depending on the signal, the neuron will fire, or you can call it activated or not. And this is just the idea of our biological neuron system. Obviously, the neurons are the one that process the information. And these synapses, dendrites, axon, will be used in our artificial neural network. So in artificial neural network, this is how it looks like. So the inputs are like our dendrites. Then we have a set of weights. This weight is like our synapses. The output is like axon. Okay. And this artificial neural network, as you see in this diagram, is introduced by these two guys over here. We call this neuron the McCulloch-Pitts neuron. And this is the first artificial neural network being introduced. And how this artificial neural network learns is by adjusting the weights in the neural network. So these weights are important, yeah, because later on you will see it will adjust this weight by learning it, okay? So what happens here, in this, we have each of this input. Each input has its own respective weights. These weights, normally we initialize it as randomly. And all this will go through a summation function. This summation function is very simple. I just take whatever input you have, multiply with the respective weight. Whatever input that you have, multiply with this, and then we sum them up. And through this summation function, it will go through an activation function. This activation function will determine the output of a neuron, whether it should be activated or not, fire or not. There are two commonly used functions, the binary step, then the other one is the sigmoid function. To make things easier, we are going to use the binary step function. So just from here, right? If your x value is greater than or equal to 0, we just output 1. If it's less than 0, we just output as 0. There are other functions that we can take a look, and I'm sure that some of you maybe heard of like ReLU, tangent H, and those so forth, right? We can use that as the activation function. But for this class, we're just going to stick it into a simple one because we stick it to the binary step function. To see this, I'm just going to use an example here. Assuming these are our input, we have 1, 0, and 0.4. And this is the weights that we randomly initialize. So weight 1 is 1, weight 2 is minus 0.5, weight 3 is minus 1. So all this will go through a summation function. So what we can do is take this, multiply with this, take this one, multiply with this, take this value, input, multiply with the respective weights, and sum them up. Once we sum them up, is 0.6. So what happens now? Check through the activation function. 0.6 is greater than 0, right? So we are going to output 1 for these inputs that we have. That's simple, okay? That is the artificial neural network. But there's a problem with this kind of neural network, because what happens is, if your input is everything 0, what happens? When you multiply, everything will be 0, isn't it? And when you have 0, then it means that no matter how also, the neural network will not learn already. It's just stuck there, stagnant there. And with this, to address this, right, we introduce what we call a bias node. Okay, we have this bias node. The input for the bias node is 1, and the bias node has its respective weight as well. And in the summation function, we just need to add this term in, the bias node times the respective weights, and then we sum them up. Now, this one here is so that to address, let's say your input is all 0, we still allow some learning in the neural network instead of just stagnant then without learning. And later on, we will see when we do the hands-on, we can see this bias node here. Now, of course, just now when we mentioned, right, how neural network learns is by adjusting the weights. At the output here, there must be a way to calculate the error so that we can back propagate the errors back to the weights and update these weights. How to calculate this error? By using the formula. So sigma is equal to the target class minus the output that we have. From this error, then we will need to update these weights over here. How to update? Use the old weights plus, now this eta here is what we call the learning rate. This is the learning rate of the neural network. It controls how fast the neural network learns. And then this sigma here is the error, and then x here is the input, okay, the input value. So we're going to use this whole flow to help us to go through how the neural network works here. Algorithm-wise, first we initialize the weights at random. So all these weights here, we initialize randomly. For each training example, we're going to compute the Y output, do the checking. If the target and output is not the same, then we calculate the error, update the weights. And we are going to repeat this step 2 until either the neural network converges or the training cycle is reached. So I'm going to show you later on what does it mean by convergence. Big example. We are going to use this example of the table, only 4 records. And this is how the design of our artificial neural network. We have 2 inputs, x1, x2. This is the target class, and the last column is the target class. And then don't forget we have a bias node. The input always 1. Then we have x1 for the input for this first column. Then we have x2 for the input for the second column. Then this is the initial weights that we have. We'll go through the summation function, just like how we have calculated earlier on. And then we will just use the binary step function, a simple one, yeah? As long as it's greater than or equal to 0, then output 1. If not, output 0. Whatever output we have, then we check whether the target is it equal to output. If it's not, then we're going to update these weights. So that is the whole process that we're going to do. To see how this is implemented, I'm going to use the table to help us to fill in the blank so that you can get some idea how this neural network works. Because of the space, I'm just going to put it as like this, yeah. So this is the initial weight. Okay, so I'm just going to put, this is the bias weight. This is the weight for the x1. This is the weight for the x2. This is the binary step function. And then this is the formula to update the weights. So let's begin, yeah. Fill up the table here. The first input having 0, 0, right? So we put in the 0, 0. This is x1, this is x2. Go through the summation function. So how to calculate the summation function? The bias node multiply with its weights 0.5 plus the first input 0 multiply with the weights here minus 0.5. And then we have the third input, the second input x2, 0, multiply with the respective weight, 1. If you calculate correctly, what do you get? 0.5. Okay, so from this 0.5, go through this activation function. 0.5 yeah, is this part here, right? So we're going to output 1. So put 1 over here as the output. Are we going to update the weights or not? Because the target and output, can you see 0 is not equal to 1? So yes, we are going to update the weights. How to update the weights? Use this formula. So we're going to calculate each of the weights, not only the x1, not only for the weights for this one, but also for the bias. The one with the bias, okay, W0 is the bias. This is for x1. This is for the weights for the x2. So let's plug in. Yeah? The weight, the O weight is 0.5 for the bias node. This is the bias node. This is the learning rate. Yeah? I'm just going to set it to 0.2 for now. but in other days, you can actually put it into other values, 0.3, 0.4, and then times target minus output. So target is 0, output is 1, so 0 minus 1 times the bias value here. The bias, this is the bias, yeah? This is the bias input. And if I backtrack a bit, this is the input for the bias, that's what? Then multiply, 0.3. Same thing for the weights for the W1. Minus 0.5, this is the weight. Then 0.2, the learning rate, times target minus the output. So 0 minus 1. And what is the input? Input is 0. Okay, input is 0. And after calculated, this is the updated weight. So what happens? We are going to update these weights over here. So this is the updated weights. Then now, next thing is continue to do a second record using these updated weights. So now here, we are going to continue the bias multiply with the respective weights, 0 multiply with the respective 0.5, and then the input 1 multiply with the updated weights, yeah? And this is 1.3. Go through this activation function. 1.3 is this part here, right? Output as 1. Target is 1, output is 1. They are the same, isn't it? So are we going to update? No, we are not going to update. We're just going to continue. Move on to the third record. Repeat the same whole process. As long as when the target and output not the same, then we need to update the weights. And we repeat the whole thing until the next weight. Yeah, we repeat this one. If we calculate it correctly, then we update this, the next weight. So this is the updated weight, and then move on to the next record and so on. Now, how does the neural network stop learning? Okay, we'll repeat, yeah? Repeat, as long as the target output not the same, we keep on update the weights. Update, update, update until where we come to a situation where the update is all no, no, no for all the records. Then we stop learning. Or this is what you call converge, right? No longer need to continue learning. No longer need to update the weights anymore because everything is good ready for now. Either it converges or the training cycle has been reached. And that's when the neural network will stop to learn. Okay, that is the idea of a neural network. So every time how it learns is keep on updating the weights as long as the target and output not the same. Okay, so that is our artificial neural network. The one that we have shown earlier on, this is what we call a single layer perceptron. This is the simplest version of a neural network, single layer. Then we have something called multi-layer perceptron, or in short, if you can see some of the algorithm, we call it as MLP. This is what we call multi-layer perceptron, and this is when we have hidden layer. So this is the hidden layer. So there's one hidden layer with two hidden neurons. This is the multi-layer perceptron. So single layer perceptron, there's no hidden layer. Multi-layer perceptron, there are hidden layer. Okay, so far okay with the neural network?
Prof, I have 3 questions actually.
Yeah, okay, go ahead.
Okay, so number 1 is the bias node input always 1?
Yes.
Or how? 1.
Yes, it's always
the
1.
bias input.
And yes.
Okay, all right. And then secondly, does the learning rate always 0.2, or we can actually
we can
modify
change. We can modify it. So normally so the learning rate is control how fast the neural network learns, right? So the higher the learning rate we put, the faster the neural network learn, but it will affect the generalization. And if you put too low, means that it's very slow to converge because it's keep on very slow, just like the kid is too slow. Why you too slow? Gotta keep on learning. Normally,
but it's more accurate lah.
More accurate but it's low. It is longer. Normally, we
Longer
will
lah.
put like 0.2, 0.3, 0.4, around this range.
But now, like, we have like compute, right? I mean, we got a lot of the computers and everything. So it doesn't hurt us lah to put it slow because we got computer to run it for us, right?
You can. So if you think that 0.1, okay, just let the computer run. It's not to affect me also, right? So let it run.
Yeah.
But just that it's slower.
Yeah. Yeah. And then another one, okay, thank you, Prof. And another one is does the weight limit the weight, does it have like a limit, like -2 to 2, or does it macam, does the weight has any limits?
No, it can be a lot of different values depending on the input value.
Okay, all right.
It can be some other later on when you do hands-on. You can see that the weight is quite large.
Okay, it can be large. It's not just like
it's not like just like this one. Not
okay.
This one is just to as an example.
Okay, all right. Okay, clear, Prof. Thank
Okay,
you.
thank you. Welcome.
Prof, can I ask something?
Yes, go ahead.
For the learning rate, does it depends on our computer performance?
Yeah,
For example,
it depends on your computer power also lah. Then secondly, it depends on how many neurons you are looking at. So let me just go back to this multi-layer, right? Of course, nowadays we have a lot of deep learning network and things like that, right? So instead of just one hidden layer, we can have a lot of hidden layers with different neurons. We have another hidden layer here. And then sometimes you might want to have another hidden layer over here. So it depends on how deep or how complicated your multi-layer perceptron, your neural network design. And if you have more hidden layers, then of course it will slow down your processing, the learning.
So the more layer we have, like the more accurate lah.
It's more accurate, yes, but it will very slow down.
Yeah. Okay.
We can even try it later during hands-on. We can try to configure the neural network, and then you can see that that's the difference when we have one simple neuron hidden layer, and then let's say we increase it to 5 hidden layer, then you can see there's a little bit changes in the performance. You can see later on. So later on, we will try to do some hands-on, and then we can configure this neural network into a more complicated one, and then we will see how fast or how slow it runs. So of course, it's depending on your computer, your laptop. If your laptop is good with a lot of high RAM and high processor, then of course it will run fast. But if not, then you will see that there are some effect in the performance later. Okay, yeah. Okay, then for the methodology, normally when we want to do machine learning, right, for the data set, we need to split the data into 2 parts, the training and the test data. The training data will be used to train the machine learning algorithm. Once we have the model, we use the test data to do the evaluation. So that's the training data and test data have to be different. Yeah, it cannot be the same so that we can really fully test the model. And this is how we're going to split the data. Normally, data, we have 2 parts, right? Training and test set. So depending on the size of the data, normally we will use 70% for training, 30% for testing. Or some will actually use 80% training, 20% testing. Depending on the size, if you have a very limited data, that means you need more training. Yeah, so you need to have increase this training size. But this is just only one split of the data. But there's a problem to this if you just only look into one split. Because sometimes what happens that we are so unlucky and we choose a very troublesome test set. Okay, when we have a troublesome test set, what happens is that everything we test, of course, it will affect your performance, right? Everything will be wrong, incorrect, and then overall it will affect the performance. But in fact, your algorithm is actually doing the correct thing. Your model is doing the correct thing, just that the data that you have in here is just unlucky, okay? You have not so good test set. And to avoid this, normally what we do is we do the cross-validation. That means we perform different training test bed and then use each of the sample in the test set for once. And this is what we call the K-fold. If you take a look at the right-hand side, this image here, this is what you call a 5-fold cross-validation. That means your data, we split it into 5 different folds. For each fold, we use different parts of the data for training and testing. So like the first fold, we use the first part for training, the last part for testing. The second fold, we train on this part here, and then we use this part for testing. The third fold, we use the first and the last part for training, and then the middle part for the testing and so on. So that this one, we can go through all the data, then we have less bias in the data, and we can evaluate our model better. So that is the cross-validation that we're going to apply later on during our hands-on. Now, once we do the cross-validation, there must be a way to measure the performance of our model, right? And this, we will use the confusion metric. It's just a table that provides the prediction result. Just like in here, this is a table of confusion metric. Row-wise, we have the predicted value. The predicted means the model that predict, yeah, the algorithm that predict. This is the actual, the column-wise is the actual, that means the actual target class. If the actual is yes, the predicted is yes, we call this as true positive. When the actual is no, predicted is no, we call this as true negative. When the actual is no, but the algorithm predicted it as yes, we call this as false positive. And when the actual is yes, but the algorithm predicted as no, we call this as false negative. We are going to use this example. Let us try to fill up this table. The one in the orange, this is actual. This is your actual target class. The one in blue, this is your algorithm that predicted the output. Altogether, we have 10 records. So now, for the actual that is yes, predicted is yes, how many of them? So let's take a look at the table here, the output. Yes, yes, both also yes, yes, yeah. Yeah, how many? There are 4. Yes, that's good. There are 4. So fill in as 4. What about no and no? How many no, no? Both also no, no. No, 1,
3.
3, right? Okay, so 3. Yeah, that's how you fill in this confusion metric. What about actual no? Play is yes.
1.
1, right? There's only 1. Okay, there's only 1. And the remainder is the actual is yes, play is no.
2.
This one, 2, right? Okay, so altogether we have this values that we have. That's how we actually calculate the confusion metric. And the first measurement that we normally use is the accuracy. So from this confusion metric, how to calculate the accuracy? Take the diagonal, 4 plus 3, 7, divided by this whole entire numbers here. In total, we have 10 records, right? How many records? There are 10 records here. So 4 plus 1 plus 2 plus 3 is 10. So 7 out of 10, the accuracy is 70%. If you convert it into a percentage, this is 70% accuracy based on this example here. Accuracy is one thing. For classification, normally we will consider 2 other measurements. The first measurement, we call it as the recall rate, or sometimes we call it as sensitivity. What is the formula to calculate this recall rate? The true positive divided by true positive and false negative. So that is the recall. What is recall? Of all these actual positive records, how many are correctly predicted by the model? So there are 4 out of 6. And if we convert this into a percentage, the recall rate is 67%. The second measurement is precision, or some will call it as positive predictive value. How to calculate this? Given this formula, we are going to take the true positive divided by true positives and false positive. This is the precision. And what this precision is about, of all these instances, that is predicted as positive, how many were actually positive? So this one, if we calculate it, 4 out of 5. So if you convert this into percentage, it's 80%. In classification, we normally prefer the recall rate to be higher because we want to catch those that is positive. We want to catch those positive cases, whether it can be detected by our algorithm or not. And recall and precision is always the inverse. One's go up, the other one have to come down. The other one go up, the other one will have to be down. And of course, there are other measurements that we can use, but these are the two frequently used metrics that we use to measure the classification performance. Okay, later on, we are going to see the recall and also the precision and the accuracy. So that's it. This is the lecture part. And later on, we will go for a short break, and then we will cover the hands-on, which is on the R, using R. Let us resume. Just to check, you can see my slide already, right?
Yes.
Okay, boleh. Okay, thanks. Okay, then we will continue with the practical part. What we need to do is we are going to take a look at one of the data set. Then we're going to split the data into two parts, the training, the testing. And then we're going to train the three models, decision tree, care nearest neighbor, and also the artificial neural network. And then lastly, we're going to use the three metrics, the accuracy, the precision, and also recall to evaluate our model. Okay, so this is just the flow for today's hand-on. And the data set that we're going to use is what we call the PIMA Indian Diabetes data set. This data set contains a collection of medical diagnostic report of 768 examples from a population living near Arizona. And all these patients, they are female, at least 21 years or older of PIMA Indian heritage. And our task here is to predict whether this patient has diabetes or not based on their diagnostic measurement. And this slide shows you all the variables. I think some of this is not something new to you all, right? Number of times pregnant, plasma glucose, diastolic blood pressure, triceps skin fold thickness. Then we have a 2-hour serum insulin, body mass index, and this is something that I know. Diabetes pedigree function. Then we have age, and the last column, the last variable here, the diabetes is the target class. The value is either negative or positive. So all these first 8 variables, these are the independent variables. And this is the what we call the diagnostic measurements for each of the patient. So how do we load this PIMA Indian diabetes? Before that, these are the packages. As I think just now I already copied it to the chat room. Please install all these packages. We need this ML Bench package because the data set, the PIMA Indian diabetes data set is taken from this package. Then we have the PyR package. This in later on you will see to use it for the splitting apply function. R part is for decision tree, and then R part plot is to plot the decision tree later. And then the care nearest neighbor is from this package called class. The artificial neural network is from this neural net package. And then we're going to use the carrot package for the confusion matrix. So we can install all these packages, take some 1 or 2 minutes. Then after that, just load all these packages. Yeah, so this is how we load the packages in R library and then whatever followed by the package name. Now, how to load the data set? So just put data, P capital, I capital, D capital. So PIMA Indians diabetes. I'm just going to make it easier. Instead of you typing, I can just copy this into the chat room. You can just copy and paste and then run one by one. When you execute data, this one you load the Pima Indian diabetes into a data frame, right? We use string here because I want to know what are the data type in the Pima Indian diabetes. When you run this second line, it will tells you all the variables are in numeric form except for the last one, which is a factor in 2 levels. One is negative, one is positive. And the third line here, summary, means to give us the 5-number summary of the Pima Indian diabetes dataset. Now, this is important. Normally, I will use this here to give me some idea about what the data is about. Now, I just want to point to you, we have all these are the variables in our dataset. The last column here is the diabetes, which is the one that we want to predict. So altogether, we have negative 500 records, positive, there are 268. So altogether, we have a 768 records for this data set. This 5-number summary is important. Yeah, take a look at the minimum, take a look at the maximum. For pregnant, I just want to see, want you guys to have a look at this pregnancy. Okay, let me highlight. Minimum is 0, maximum is 70. Now, I'm not too sure from a medical point of view, but from a layman point of view, for someone to be 17 times pregnant, because pregnant here means the number of times pregnant, yeah? Number of times pregnant here. This one, the first one. But from a layman, I'm not too sure whether is it doable or not. Is it possible or not? Now, what do you think? Do you think that it's okay for someone to pregnant maximum 17 times?
From my
No.
experience, the maximum number is around 10.
Around
From
10,
my
right?
experience.
From your experience, you got under 10, okay? From a layman, I think is not possible lah. But from majority of you, no. Okay, so let me just share with you. I have a chit chat with one of the doctor. I think in one of your, I think the earlier batch, I think 2-3 years ago, there was this doctor that said that, hey, why not? It's possible to be 17 times pregnant. Then I asked this doctor what happens. Why do you think? And then she was sharing with me that said that it's possible because we're looking at the Pima Indians heritage, and this number of pregnancy doesn't mean that, to his opinion, the number of time pregnancy, it doesn't mean that it's really like 70 times giving birth. It can include the number of miscarriage. It could include something else. So 17 to him maybe is possible that he might accept this number. So like this case here like that, right? Normally we will discuss whether should we ignore this kind of records? Should we consider this kind of record? So if you think that 17 is not possible and you think that we should not consider this record, then we should eliminate this 17, this record of 17 times. And also, there are a few things that I just want to check. Yeah, is it possible to have plasma glucose minimum 0? Then we have this pressure 0, tricep 0. I'm not too sure. Body mass index BMI 0. Not too sure. Boleh ke?
No.
Not possible.
Not logical.
not logical, right? Because
Not logical.
from a layman like me, not medical person, yeah, I will. To me, when I look at this 000 means something is not so right. To me, I was think that it's like 2 something, that kind lah. So I'm not too sure. If you think that 00 is maybe the data set is not right, it's not possible to have 00, then we should eliminate this. So normally when we do machine learning, data understanding is very important because we need to clean the data. We need to pre-process the data so that when we pass this data set to the machine learning, it can learn the correct thing. Because if you're not right, if you consider this, when you train the machine learning, no matter how, let's say machine learning give you 100% accuracy, you cannot trust because your input is not correct. So we have to be careful a bit to check on the data set to see whether it makes sense or not. And this 5-number summary, this summary here actually provide us an indication. Okay, so let's assume now, okay? Okay, let's make an assumption here now. We are okay with this 17 pregnancy. We are assuming now we are okay with this. But for this glucose, pressure, tricep, mass, body mass index, yeah, if it's 0, we do not want to consider this. So what happens now? We want to do a simple pre-processing first. So I have this code over here. I only want those glucose. Okay, this one means not equal. I want some value. So those glucose, tricep, pressure, and mass, if it's 0, I'm not going to consider those records. So like this one, tricep is 0. I'm not going to consider this. Then we have a tricep also 0. I'm not going to consider this record. And then this the 8 row, they have pressure 0, 0. Also, I'm not going to consider record. I only want those record that has value. And this is how the code I'm going to extract it. So I just call it as DF1 later on. And then this is what we are going to consider, those glucose, pressure, tricep, and mass that has values. Okay, this is what we're going to do. Now, I'm just going to unshare this so that I can come to my R and show you how it actually runs in this pre-processing steps. So this is my R Studio. So we have really done the data. So I'm just going to load the data. So this is my PIMA Indian diabetes data set, right? And then the string here, as I mentioned, it just tells you that these are all numerical. All these are numbers. Then the last one is the summary, as you can see just now in the slide, to give you some idea what is the minimum and maximum. Then now, because I want to deal with the data frame, I just pass this PIMA Indian into a data frame. I just call it a DF here. So I'm just going to run this. Okay, so let me copy this part here so that you can run it at your site as well. So run the DF to load the PIMA Indian diabetes into the DF first. And then later on, we are only considering this. So run this DF and then run this so that we only extract those records that have values for the glucose, pressure, tricep, and mass. So if you run this, take a look at your DF1 now. You already only have 532 records. So just do a quick check. Can you see all these records? Glucose, pressure, tricep, mass, there are some values. There's no 0. Except for insulin, because I think insulin 0 is still okay. I do not know. Okay, if you think that insulin 0 not okay, then you just eliminate. But if not, then we just consider we allow insulin to be 0. Okay, the rest all are having values. Yeah, so you can just go down and see these are all these having values. This is just a simple way to get the records without 0. All these 4 columns. Okay, now then going back to my slides, let's see how we're going to split this data into the training and test set. We have a total, our DF1, the total records is 532. Because we have limited data, right? So we're going to have a split the data into training test set. We take 80% for the training, 20% of the data for testing. Okay, how do we do that? So let me just explain about the codes first. Enroll DF1. Enroll, the function enroll here means to get the number of rows from our data frame. So this DF1 has 532. Okay, just enroll DF1 will give us 532. Because we're looking at 80%, right? So times 0.8. 532 times 0.8. Let me just calculate this in my R. 532 times, let me just do a quick 532 times 0.8, 425.6. Flow here means we are only taking the first few integer before the decimal point. Okay, before this decimal point, we only get the integer before this decimal. I think there is a 1 decimal here, so let me just highlight like this. Okay. So S row, I put it into a variable. I just call it S row or whatever name that you want. So say it's 425. So this is my training data. This is my test data. To training data, I'm going to get all the rows from 1 until S row. That means 1 until 425. That means my training data consists of row number 1 until 425. That is my training data. Test data, 425 plus 1, that means 426 onwards until the last row. Okay, the last row is 532. So 426 until 532, this is what we call the test data. And this is how we split. So in the future, let's say we want 70 and 30%. So what you need to do is just change this one to the respective percentage. So if you want looking for 70%, then you put 0.7. If you want 60%, then you put it at 0.6. So this is a flexible, you can change it accordingly. But for now, we're going to use 80%. Now with that, I'm just going to copy the codes and you can run it at your side. So let me just get it in the chat room. So just copy and run it. And you can see that now your training data. Okay, let me run on my side. The training data, you have a 425. Test data, you got 107. So after running this, your training data, okay, maybe this has a total of, okay, let me just double check again, 425. And then your test data has a total of 107 records. So do you get this at the moment before we move on? Can, yeah, other than? So your train data is 107, and then your test data is 107, your train data is 425 records. Okay, can anyone haven't executed yet or got some problem with your codes?
Okay.
Okay, yeah. Okay, so I'm just going to move on. So with this training and test that we have gone through, so now we are in the position to build the model, okay, to train the model. The first algorithm is the decision tree. Now, every time when you see a slide that has a square rectangle box in gray color, this is the function, okay, the function. So we are going to use the rpart function to build the decision tree, because the decision tree, the package they're going to use is rpart, so we're going to use this rpart function. Now, formula, it means which variable, okay, the variable that you want to predict and the variable that you want to consider. So the variable that we want to predict is this diabetes. Okay, so if you can go back to we want to predict this one, right? So diabetes. So we put the diabetes, a tilde sign. Now this dot here means all other variables, all the variables to do the prediction. Means I'm going to consider all these variables to help me to predict whether there is a diabetes or not. It's a short form, right? Dot means to consider all the variables. Then the parameter for the data means the training data. So I'm just going to pump in this training data, because you want to train the model yet first, right? So the train data is the one that we get from here just now. That is. The next thing is class. The method is class. Why class? Because we are doing classification. Okay, we are doing classification, so that's why it is called class. And the last one is PRMS is parameters, in short, because we want it to use it as an information gain. So this is how we actually use and specify that to run the decision tree using information gain as the splitting criterion. Then this is how we specify list split according to information gain. And we are going to call our model the output. I'm just going to use this DT, short form for decision tree model. PRP here means to plot the decision tree model that we have trained. So let's go ahead and then try to build our first model. So let me just go to my RStudio. Just hang on first, yeah. Let me just copy these two lines to train the model. So just execute the first line to train the addition tree model. After training, then you plot this model. Can you see on the right-hand side? Okay, I know that some of you maybe might not be able to see. If you cannot see your addition tree, what you need to do is just enlarge the bottom part so that you can see this decision tree, the output. So from this decision tree, you can see that the first question that we ask is the glucose. Is it less than 155? If yes, then we go on the left-hand side. If not, we go to the right-hand side. Then the following question that we ask is the body mass index. Is it less than 26? If yes, then negative. If not, then continue asking what is your age and so on. And this is how the decision tree look like. It might not be that beautiful, but of course, you can add in some more parameter to make it more colors later on if you want. But this is just only a simpler one to just give you some idea about the model of the decision tree. Okay, that's how we visualize. If you think that is hard to see, you can just zoom in to get a bigger decision tree models. Okay, so this is the decision tree model that we have created. So later, we are going to go on to my slide so I can show you how we can actually do the prediction. Let me just go back to my slide. So once we have this model, the next thing is to do prediction. Okay, so we use the function predict. Pass in 3 parameters. The first one is the object. Object is your model. Your model. We are going to pass in this decision tree model. New data is your test set. Okay, this is your test data. And then type, we are doing classification. So type is equal to class. And then the output, I'm just going to put it as, I just call it as DT predict. Okay, in short, prediction means pred. So DT pred, or whatever name that you want. And then later on, after we do the prediction, then this is the predicted output, the predicted output. Then we are going to use the package confusion matrix to help us to calculate the confusion matrix. In the confusion matrix, there are 3 things that we need to specify. One is your predicted result, which is DT pred. What is your actual target class? Your actual target class is from your test data. And then this $sign means that you are referring to the target class column, the type it is. And then don't forget, what is your positive value? Because confusion metric, we need to know what is your positive. Is it 1 or 0, or is it positive or negative? So if you go back to your data set, right? This is the value of your data set. The positive value is the POS, POS. So we need to specify which is the positive value, which is POS. Then with this, after you execute, then you will see this is the output of your confusion matrix. This is the table, your confusion metric table. This is the predicted. The column wise is the reference. Reference means the actual. Then this is the accuracy. Okay, I'm just going to highlight the accuracy of your decision tree. Other measurement like sensitivity, this is your recall. And then your post-predicted value, this is your precision. So this are for now, okay? We are just going to take a look at these 3 measurements. So let me just write it out here. This is recall. This is your precision. There are other measurements as well we can consider if you want to have more measurements to evaluate your classification model. But for now, we are just going to concentrate on these 3 metrics. Okay, with this, let me just copy the R codes to you, and then you can have a look at the confusion matrix. Okay, so these are the 2 lines to do the prediction, to test using the test data, and then later on to calculate the confusion matrix. Okay, so far okay kan? Got any errors in your decision tree?
Okay, no error.
Okay.
Okay, no errors, yeah. So you can plot the confusion matrix, yeah.
Yes.
Okay, that's good. Okay, now I'm just coming back to my slide. So we have this result. Okay, now let's move on to the next model. The second model that we're going to create is the k-nearest neighbor. Now with k-nearest neighbor, like just now, remember we used actually the Euclidean distance, right? Now, sometimes we will have variable with very large range. The range of the values very large. And when we have a large range of values for certain variables, they can actually dominate the distance calculation. To avoid this, we need to scale the input variable value to a range of 0 to 1. And one of the techniques that we use in machine learning is what we call the min-max normalization. So given this formula here, this is actually use it to normalize, or you can call it a scaling, scale the variable into a range of 0 to 1. And how this formula works is that, okay, so let me just try to visualize a bit. These are the Pima Indian diabetes data set that we have, right? We take the first value minus the mean of this entire variable divided by the max value minus the mean of this particular variable. So, and then we do the same thing for this one, and all those continue. And how to represent this in the function. So this is how we do it in R, yeah? I just call it as normalized, or whatever name that you want. I just call this a function normalized. So I just put a function x, curly, and this is exactly the formula, right? Exactly this one here. Nothing fancy, just straight to a point. So I'm just going to return. And this is how we do the normalization, the function. Don't worry about this. Later on, I will explain a bit more about this. So with this, I'm just going to unshare this. Okay, I'm just going to share back my RStudio so that I can we can run it together and have a look. First thing, I don't want to mess up with my DF1 because the DF1 is my decision tree, right? I just leave it. I want it to have a new copy of the data frame. So I just put DF2 equal to DF1. Okay, I'm just going to copy this one to you in the chat room. You can just replicate this. DF2 equal to DF1. I just copy exactly, yeah. Then I have this normalized function. Okay, let me just copy this to you in the chat room. Okay, let me just run this first, yeah. DF2 equal to DF1 is exactly the same as DF. So if I open up my DF2 and DF1, they are the same thing, okay? Because it's a copying. And then run the normalized function. How to run the normalized function? You just copy this whole function, run. Okay, copy this whole entire function, run. Once you executed, can you see in your environment? So let me just pull out this one. Can you see there's a normalized function? That means you already executed this function here. Now, next thing is, if you take a look at your data frame, right? I only want to normalize or scale this variable from column 1 until column 8. We don't need to normalize the last column because the last column is our target class. We don't need to normalize this one. We only normalize those that is independent variable. All the variable except the target class. In here, I have this df2. Okay, so what happens here? Let's take on the right hand side. I use the apply function, lapply function. Basically, I apply on the df2 column 1 to 8, and I call this normalized function. And then the output after normalize, right? I just replace all the value from column 1 until 8 for the df2. So this is what we are trying to do now. So let me just copy and paste it into the chat room. We are looking at df2 now, yeah? So if I run this, okay, let me run that. And then let's open up the df2. Can you see now? It's already normalized into a range of 0 to 1. Okay, all these columns except the last column here. Compared to the df1 is in this numerical form. But in df2, now these are in scaled form. Yeah, so far okay kan, the df2. Anyone not able to do for the DF2? Okay,
Okay.
either okay kan DF2 it should be something like this, yeah? I'll
Mm.
just give you some idea first, yeah? Okay, with this, now we need to split the data again because now we are looking at this DF2 for the normalized. So we want to use this one to train our care nearest neighbor. Here, same thing. This time I'm looking at DF2, the same thing as what we have gone through just now. S1 until S row, which is 425, as my training data. And then 426 onwards until the end of my DF2, this is my test data. Now this time you can see, I call it as N. N here means normalized. Test data N means normalized. So I'm just going to copy this to you, and you can split the training and test data. So let me just run these two lines. So you can see in my training data N, now this is my training set for the normalized data. This is my test set for my normalized data. Training data N. Data N is this one here. The normalized, and then the test data N, which is this one here. So test data N, you have 107 records. Train data N, you have 425 records.
Sorry, Prof. Can I ask something?
Yes, go ahead.
So basically, when we normalize the data, they're using the formula that we mentioned above, right? The
Yes,
X
correct.
minus minus.
Mm.
For the variables, all are numerical. What happens if the variables are categorical? Can we
Categorical,
combine?
no need, you just leave it.
Leave it
You
like
need, yeah, you only do it for the normal, for example, like this one here. Let's say the F1, right? Because this one you have a long range like 0 until 17. So I want to normalize it so that it become 1 to 0 in the range of 0 to 1.
Okay, thank you.
And we normally normalize it for other variables except for the target class. Okay, then after that, okay, so now let me just go back to my slide just to elaborate on the care nearest neighbor, how we actually run this. Yeah. So we already have a test data N, we have train data N. Care nearest neighbor, use this function KNN in lowercase. There are a few things that you need to pass in for the care nearest neighbor. First is the training data set. So our training data set, just note here, we are using train data N. The normalized version, not the train data. All the rows, column 1 until 8. Okay, you need to specify this for the KNN only on the training. For the variables that you want to, the independent variables. Yeah? Then the test set here is again same thing, the normalized test data. All the records, column 1 until 8. Okay, you need to specify this for the care nearest neighbor. CL means the class, which is your target class. In here, the target class is the 9 column, right? The column 9. Okay, so if you visualize your table, your data set, you have a column 1 is the pregnant, and so on. The last column here, the diabetes, is column number 9. So you need to specify the class is at column number 9. And then we are going to use k equal to 7. So this k equal to 7 means we are going to consider 7 nearest neighbor. You can put 5, you can put 3, you can try it on later, but for now, we're just going to use it as 7. Then after that, straight away, confusion metric, just like what we have done for the churn tree. I call this output, KNN prep, pass into your confusion metric. then you need to specify which one is the class, the target class, and then the positive, which is POS. Now, let's see. Unlike decision tree, okay, if I backtrack a bit, can you see decision tree? First, we need to do training. Then secondly, we do the prediction. But for KNN, we don't have these two steps. There's only one step here, and straight away we can do the confusion matrix. So that's why just now during the lecture, K-nearest neighbor is a lazy learning because there's no explicit training process. It's everything lumped into this one line of codes, and then after that, you do the confusion metric evaluation. That's it. And let's come and take a look at our R code, and then let's execute this K-nearest neighbor. So coming to here, so I'm just going to copy these two lines in the chat room, and then you can run this K-nearest neighbor. Okay, let's execute. So I'm going to execute this part. And then I'm soon going to execute the confusion matrix. So we can see the confusion matrix. And then, of course, this result here, you can compare the accuracy. Is it better than the decision tree or not? And then the recall rate and the precision. If you want 5, you can change it to 5. If you want 3, you can change it to 3. You want 9, you can change it to 9. Yeah, so this one is up to you to define. If you want 5, you can just change it to 5 and we run this whole thing. And then we plot the confusion metric. So then you can actually compare, is 5 better? Let's say we just look at the accuracy, 80.37. Earlier on is 77.57. So it seems that K-nearest 5 is better result compared to the K-nearest 7. So later on, you can play around with these parameters. And this is about K-nearest neighbor.
The decision tree is better lah.
Decision tree is correct. Yes.
0.
So that's why correct. So later on we will compile all the results together, then we will see at one go. Okay, coming to the K-nearest neighbor, of course, as I mentioned, this one, the parameter here, you can change it later, and then you can try different nearest and then see which one is the better one. The next model that we're going to train is the artificial neural network. So we have done decision tree, we have done the K-nearest neighbor. This time we are going to take a look at the artificial neural network. We're going to use the neural net function, the package here. Formula here, specify which one is your target class, which is diabetes. Tilt sign. Now, for the variables, you can use dot here. Earlier on for decision tree, we use dot, correct? Okay. Here we use dot. That means all variable short form. We can also use dot, or if not, we can actually specify like pregnant plus glucose plus pressure plus all the variables. If you only want to consider 3 variables, so let me just erase this a bit. If you only want to consider pregnant, glucose, okay, let me just, and also pressure. So you can just put pregnant plus glucose plus pressure, and then you don't need all this. I'm just giving you some example how you can put in the variable instead of considering all the variable. You only consider this pregnant, glucose, and pressure. Or if you think that you want all, but we are lazy to type the whole thing, right? And then just put a dot. Also okay, just like what we have seen in the decision tree. Something like this, okay? You can do something like this, also okay in the neural net. Okay, then specify the training data. So let me just erase all this first here. Specify the training data, which is still normalized because in the artificial neural network is based on weights, right? There's some calculation over there, the summation function, all this thing. Use the normalized train data. Then this hidden, how many hidden layer? There's only, I just put it at 1 first because it makes things easier. Later on, we will change this hidden layer. And then this linear output, we're going to put false. Why? Because you want to use activation function as the output. And then how to plot this neural network model? I call it as NN in short. So just use plot and then we can see the neural network. Okay, this is the neural network. Yeah. Then of course, same thing like what we see in decision tree, predict, put in the model, put in the test data in the normalized form, and then put in the class because we are doing classification. And this is what we are going to do for the artificial neural network. Now, let me just go to my RStudio so we can run it together, and then maybe we can change some configuration of the neural network. Let me just share my RStudio again. Okay, let me just copy these 2 lines and pass it to you in the chat room. Okay, let's run this neural network. And then when you plot, there's a pop-up window in case you are not aware. Okay, this is how the neural networks look like. The one in blue, if you take a look at the plots, right? The one in blue, that is the bias node. And then all this like on the left-hand side with the arrow pointing to it, these are all the inputs. And those numbers at each edge, right? On top of each edge, these are the weights. Okay, that is how our neural network looks like. Okay, then we do the prediction, right? So let me just come here. There are a few things here because there are a few lines of code. Let me explain first so that later on we can run it together. So let me just try to do this one here. Just now we have gone through the predict, right? I just put it as predicted, yeah? So I just run this code. I'm just going to show you what's happening. If you take a look at my console here, I'm just going to type the predicted. And this is the predicted output of the neural network. Let me just scroll up. Now, there must be some transformation over here because I want to be a negative or positive. And I have this if-else function to say that if the max column, the value of this max column is at this column 1, then our output negative. If the max column is not in 1, is in here, then our output positive. So this is the if-else statement here trying to do. So if the max column, that means the value of the max column is in the first column, output negative, if not, output positive. And this is what I'm trying to transform this output to this one here. So let me just run this one and show it to you. And let me show you this NNPrep. Can you see now? I'm actually transforming to positive, positive, negative, positive based on the predicted value of your neural network. Okay, so this is correspond. So the first one is a positive because it's at this column. Second column also, a second row is also positive. The third row is negative. That's why if you take a look at the output, the first 3 rows, positive, positive, negative. Okay, so that is what we are trying to do. Now, next thing is to do the confusion matrix. Same thing like what we've seen before, just that for this NNPrep, because can you see this character? This is a character. Double quote means the character. So we need to factor it out so that we can do the comparison. So let me just run this. And this is what the confusion matrix looks like. Now, before that, let's say during your exam, you try this and you've forgotten to factor it. There is an error. I'm just going to show you the error. So let's say I just enter, Then he says that data and reference should be factored within the same level. That means that gives you the indication that you need to factor your predicted output. Okay, so just take note, for neural network, you need to factor it out because when we do the transformation, it will be in a character format. So if you can, if you want, you can do an NNPrep string. Then you can see that it's in character format. So you need to put it into a factor so that the confusion metric, they compare these two. So I'm just going to copy these 3 lines of code into the chat room. Okay, you can try to run it. This is the confusion metric of the neural network. So neural network accuracy 81.31, recall is 66, precision is about 78. Any error on your side? All good?
Yes.
All good.
All good, yeah. Okay, now, maybe you don't do it on your side. Maybe I will change now at my side, yeah. Because I think someone just now was mentioning, can we do more? Because now we got a better machine, right? So let me just change this to 3. And then we run this. Okay, now I'm going to have one hidden layer with 3 neurons. So let me just run this one, yeah. Okay, it seems okay, right? Okay, let's just hang on. It seems okay because it's quite fast. So let me just plot this one. You can see that now it becomes more complicated because we have one hidden layer with 3 neurons. Now, what happens when I want to have more hidden layers? So I'm just going to put C, yeah? Let's say, let's start something smaller first, yeah? 1 here means, that means the first hidden layer, 1 neuron. The second hidden layer, 2 neurons. So I'm just going to run this one, execute dulu, yeah? Can you see it actually takes some time to build the neural network? It actually slower already. Compared to just now 1, it's like very fast. When I run this, it's slower a little bit. Okay, let's see how the neural network learns. Okay, so I'm not too sure whether you can see my screen or not. So this is the input. 1 hidden layer with 1 neuron. Second hidden layer with 2 neurons. Okay, now become much more complicated already. Now let's try to increase some more. Hopefully my machine can work. Let's say I put 3 and 2. Okay, now let's time this one. Yeah? We are now have a more hidden layer with more hidden neurons. Yeah? So let's try this. You will see that it actually takes some time to execute it. Sometimes you might have message to say that it cannot converge, it cannot learn because we have too little data. So you can actually play around with all these different architecture of a neural network. Of course, for my case here, it's actually learn quite slow. So you can see, sometimes you can see this output, yeah? You say that it did not converge. That means maybe your data not much for it to learn. And then maybe after halfway, it just cannot learn some more already. So if I just plot it because I cannot, because it cannot converge. So this one, maybe you either increase, you get more data so that it can learn better, or if not, then you need to decrease the number of neurons. So maybe 2. So you can, this is how actually for the different layers. I'm not too sure whether this one can. I think this one should be okay. Okay, you can see that as the more neurons, the more hidden layer, it actually slower down the training of the neural network. And you can, this one is still, this one is okay.
Prof, how do we decide between the number of layers and the number of neuron? What's the consideration there?
A very good question. There's no rule to say that how many neurons, how to decide. It's actually based on the data that you have and how many hidden layers. So normally when we have, let's say we're talking about image, right? Let's say you want to produce some kind of face. Let's say your image about face. The more layers, then the neural network can actually do the face recognition. The better is it. But if you have like, let's say we are looking at structured data, normally we don't do too much hidden layer because we do not want it to be, because as you can see, right, the more layers, longer time to train. And is it really important to have more layers for your structured data? And you can see, actually, you can compare the result, right? If you have more layers, it doesn't mean that the better one. Sometimes it may be worse. And then this one you have to try. And that's why in the neural network, you have a search algorithm. You need to apply the search algorithm to see which one is the better configuration for you. You have to run that search to see which one is the better. Normally, we will have two hidden. and then not too much to 3 layers. We don't normally go beyond that. Unless you want to try different architecture on the deep learning, we have different layers, different structure. But for multi-layer perceptron, normally 2 layers will be good enough already. Okay, so hopefully can answer, because this one is very hard to answer whether which one is the better one, because it depends on the data and how complicated your data is, how many rows.
Can we like do several model, like different layer, different neurons, and then see which one actually is the optimal one?
Can, that's why, okay, either you do it manually or there's an algorithm, you can use packages to help you to find the best tuning algorithm, the parameters. You can. So either you do it manually, you do one, then you capture the result of the hidden layer for one, then you try 2, and then you try 3, and then you try 1 hidden layer with 1 neuron, the second layer with 1 neuron. Then you increase slowly 1 by 1, or you do this one or increase the other one. And then later you capture on, and then you have a look at the accuracy, your precision, and then record for each of the configuration. Or otherwise, yeah, there are some methods, some packages you can use, but it will take some time because the packages will take some time to run. It will run until it will tell you what is the best configuration for this data set that you are looking at.
Yeah. Prof, like what's the like conceptual understanding behind the layer? Because we already understand that from this variable we can predict the class of the target class or the target variable. But how does we understand these hidden layers? Meaning what do they do in terms of conceptually lah?
Okay, so maybe I will come back to my slide. So just give you some idea. Let me see my neural network. Let me just jump to my neural network. Okay, it's a single layer perceptron. Wait, let me just get back to my lecture slides. Let me just come back to this. I unshare this. I'll come back to my sharing on my slide for the lecture. This is a single layer. There's no hidden. Okay, so let's say we do something like hidden layer lah. Let's say we want to do some kind of compression. Okay, let's say we talk about image. We have, okay, let's say maybe here I will have some input lah, whatever, some eye, some, I don't know, some nose, some, okay, my drawing is not so good, and some hair, whatever inputs. And we want to produce the output, an image of the person, okay? If we have only one hidden layer, maybe until this part, it can only reconstruct until maybe half of the face. It depends on, maybe it only can reproduce until the eye part. If we have another layer, we can learn to reproduce it, maybe add one more, the nose. And then if we have another layer, a little bit more, so that it can learn more, so we can actually have a more output for the representation of the image. This is just one example. If you have only one layer, as I mentioned, right, for image, let's say, for example, maybe you might not get the whole picture. You can have a very fussy classification of the face. So maybe you can get the eye, maybe certain part of the nose, but not the full nose. So the idea of hidden layer is just that how you want it to learn a little bit more. It's just like, okay, I'm just putting you in layman. It's just like we are teaching our kids, right? This is red color. This is blue color. Okay, then this is the green color. Okay, maybe something like that. Okay, but in the multiple layer perceptron, this is red color. In the second layer, oh, this is a variation, and this is maroon. This is a brownish red, and then this is maybe some other color. So you can learn more variation of the colorings. So that is the idea of the hidden layer, so that you can have a longer, not longer, but a more deeper understanding of the learning process.
Yeah, but the variable we use is same, right? I mean, from the beginning to the end, even though it's different layer, but the variable, the number of the variables of each is the same. So meaning we added more like a mathematical calculation lah for it
It's just like,
to
okay, so it's just like
achieve?
here, because we are looking at structured data. So our data size we have is just only 522 records. There's not much of variation in the data itself. Maybe in future, we might have 5 million of records. Maybe we might not just only consider the 8 variables. We might extend it to maybe, I don't know, maybe 20 variables with 500 million records. In order for this to learn, because like sometimes if you are just single layer, just one part of learning, there's not much, you cannot learn deeper. So this one is, it's just like us, right? The lecturer or teacher just ask, okay, study this one, yeah? Then some of you all will just study surface, like, yeah, teacher asks us to study this one, then we just study. But some of you all will go deeper, right? Okay, I don't want to just study, I want to know what is happening in and out. So the multi-layer perceptron, the hidden layer, will actually help to studying deeper, understanding the connection between all these data that you have. That is the reason why we might have one hidden layer. It's like you are studying deeper to understand the connection or the relation between the variables that you have.
Okay, Prof. Clear, Prof. Thank you.
Boleh kan? Okay. Okay, let me just coming back to where we are. Okay, so just now we are talking about the neural network, right? Okay, let me just come back to my tutorial slide. Tutorial. Okay, this one. So once we do the 3 models, then of course this one is just to show you this is one neuron. Just to recap, this is one neuron, one hidden layer with one neuron. The one in blue, these are the bias node. Okay, these are the weights of each respective variable, and these are the inputs that you have. Then this is 2 layers, one hidden layer with 2 neurons. So there's one neuron here, one neuron here. If we compound together, this is, we are looking at k equal to 7. So which one do you think that is a better model based on the data set that we have? Is it decision tree? Is it k-nearest neighbor? Or is it artificial neural network?
Artificial neural network.
Okay, overall, it seems that artificial neural network is slightly better, right? Although not significantly, but slightly better. So this will be a choice. But remember, we are only doing one split of the data. So in order to accurately know the evaluation, we need to do cross-validation. Now, from now, it's just that it seems that based on the 3 model, it seems that artificial neural network works better in terms of accuracy, in terms of recall, and in terms of precision. The next thing we are going to do is the cross-validation. Okay, I'm just going to do a 10-fold. What we are going to do, we have our data, right? We are going to divide it into 10 different folds. For each fold, I'm going to use the first part at the testing, the remainder training. Until the last fold, the last part here is a testing. The one in the white color space here, these are used for training. For each fold, I'm going to calculate the accuracy. Another fold, another accuracy. Later on, I'm going to average out the accuracy and see the performance. To see this, I'm just going to run it from an algorithm point of view, from the back end. Is actually what happens. And this is what I'm trying to do here. Because I'm doing a 10-fold, so I'm just going to set k is equal to 10. Okay, before that, if you see majority of my codes, I use equal, right? Sometimes I know that when you write codes, you want to use something like this, right? Okay, maybe I write it. You can draw it like this, but I like to use equal simply because it's less typing. You can call me lazy lah. I just put it as equals because it's 1 step instead of 2 steps when I write this sign. Either way is fine, yeah? Then I create a vector of, I call it as decision tree accuracy, replicate NA until 10. So it means that this is how my DT accuracy works. For each fold, whenever I calculated accuracy, I update the accuracy for each of these fold. Then later on, I'm going to average out the accuracy for this decision tree. So let's say, for example, we run the first fold. the accuracy is 80% that I'm putting in. The second fold, the accuracy is 60%. Third fold is 70%. Fourth is, let's say, 50%. I just update accordingly. Then after that, what happens now? I'm going to use the split function. This split, basically what I'm trying to do is, because I'm using decision tree, yeah, I'm just showing you decision tree. I'm going to use the DF1, the unnormalized one. This split is basically from the data, we are going to cut it according to 10-fold. That means the entire data that we have, cut it into 10 different folds, just like this diagram here. And what I will do is, now I will run a for loop. This loop is just an iteration, yeah. K is 10, yeah. For each fold, for each iteration, yeah. What I will do is, I use the multiply, take whatever in the first fold. Let's say the first fold is I, yeah. So this is I is 1. Take the first fold, which is the test set. I call it test set. And the remainder, minus I here means -1. The remainder, minus means the short form for the code lah, to means that those other than 1, yeah. So those other than 1, that means all this lah. This will be put for training. So this is my test set. All these are my training. And this is what I'm trying to do here. Now within this, after I did the multiply is just a function to do manipulation in your data frame. Within the for loop, once you have multiply, if you see your records, right, you will have this automatically created ID column. I set it to now. Now means that I do not want to consider this column. I just want to remove that in my existing data. So that, which is the reason why I have these 2 lines, now. That means I just set it to now means that I just remove this column. I do not want to consider this. After this, right, within the for loop, we still consider, let me just continue, just like what we have done earlier on. The R part, your code, right, that we use, put it inside the for loop. This time, we are using the training data from this one here, yeah. The rest all no changes. Then same thing, we have seen this code before, predate, pass in the DT model, which is this model here. Use the test set, which is this test set here, that we split there for the each fold. And then after that, do the confusion matrix. This time, because confusion matrix is like when you run, just now you see there's a lot of different matrices, but we just want the accuracy. So I'm just going to get this accuracy from the confusion matrix. And then update to the DT accuracy. So if you run 1 equal to 1 until K, 1 until 10, so if 1, this one 1, then you update this particular vector. If it's 2, then update this record. If it's 3, then update this. When it's 4, update this record, and so on. And this is what we will do in backend. With this, I'm just going to come back to this R code. Don't worry, I will share this code with you. So let me just come to my R Studio. Okay, let me just clean a bit. I'm just going to copy the first 3 lines first in the chat room. Let's run the 3 lines here. So this one, run. Then this one, DT accuracy, run. So if I put DT accuracy in my console, can you see it's a vector of 10 with NA value, that means no value inside lah. Then here, I split the data into 10 different folds. So this one is 10, yeah? So I just run this. If you want to see your data, how the folds look like, this is 1 fold. It's panjang, yeah? This 1 fold, the record. This is another fold. Then if you go scroll up some more, this is another fold, and so on. Okay, so that is a different fold. Now this part inside here, I'm just going to copy this for loop in the chat room, just copy and highlight the entire for loop to run. Okay, let me just copy this for loop, yeah. And paste it. When you copy this whole thing, run. Okay, let's take a look at your DT accuracy. For each fold, it will calculate the accuracy. Can you see this is the accuracy? So how to get the average? Just mean DT accuracy. And this is the average accuracy for the 10 fold for the decision tree.